Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, I'm very happy to introduce. We are very happy to have here Alan Sly. Alan was a student of Elkanan Mossel and is now a postdoc at Microsoft Research Wormald. He's done some great works, and in particular this work which we'll hear about also won the Best Paper Award at the upcoming Fox.
Yeah. Thanks very much for the invitation to come and talk and visit here. So I'm going to start by I guess the first third or half of the talk will be just kind of talking about some of the things that previously been done in terms of phase transitions and computation, and then I'll talk about the new results. But because I think there's so many interesting sort of connections between phase transitions and sort of hardness of certain problems, and there's a lot more to be understood about it. So I'll say a small amount about random constraint satisfaction problems, but I mean you have Ricardo here, who's like one of the top experts in it. So I just want to say a few things to for context. I'll say a bit about how phase transitions affect Markov chain Monte Carlo algorithms, and then talk about the problem of the hardness of, or when is it hard to approximately count independent sets. Okay. So first of all, just what is a phase transition? So I want to be pretty vague about this. So in physics, I guess it's a transition of one state of matter to another, so something like water freezing into ice or boiling into steam as you vary the temperature. And in kind of the random combinatorial models that we'll be interested in here, I kind of just mean as you vary one of the parameters, you have sort of an abrupt change in the properties of the underlying distribution.
What is enthalpy?
Enthalpy.
It's entropy or it's something?
Good question. This was just borrowed from the Wikipedia entry on phase transitions. I don't know if any physicists in the audience can help out on that, but thanks. Yeah. Okay. So, all right. And so the kinds of some of the kinds of things you can look at are for random colorings or other random constraint satisfaction problems, or the easing model, and the main part of the talk will be on the hardcore model, which is a model of random independent sets on graphs. Okay, so why do phase transitions sort of relate to computation? Well, I guess the question is what changes after a phase transition? And so so lots of things could happen, but a couple of examples are, say, the distribution could go from being, in some sense, unimodal to bimodal or multimodal, and this is, or sort of clustered in some sense. And another thing that can happen is that you start getting long-range correlations between the values at one set of vertices and the other. So you can say, do distant vertices of this graph, other colors of a random coloring, correlated, or are they basically independent with distance?
Those two things are very related to one another.
Very much so. And both of these properties can lead to kind of a lot of the most simple algorithms, at least, failing to work. So Markov chain Monte Carlo algorithms will tend to stop working when the distribution becomes bimodal or multimodal, and kind of greedy search problems might start to fail in this case as well. Because you can find yourself in, say, a local maxima which isn't the global one. Yeah?
You're saying after phase transition becomes unimodal, so you're thinking of a phase transition that sort of goes down in your little picture, like from, say, liquid to solid?
Sort of going to multimodal.
Well, okay, one side will be unimodal and the other.
Corresponding to multimodal.
Yeah, so these were both multimodality and long-range correlations tend to go hand in hand, I guess. Yeah. So
let's say I'm looking at the phase transition from liquid water to ice.
Okay.
Which one would be the unimodal one, and which one would be the bimodal one, or or it's not that simple.
Okay. No one's ever asked me about actual physical models before.
You lower the temperature, you go to multimodal.
Thanks.
It's a good
Okay.
thing to have a diverse audience.
Yeah, no.
Well, I mean, there is a hint, right? Because when it's multimodal, you say there are frozen variables.
Very good. Okay, and so it brings us on to like random constraint satisfaction problems. And like in the last decade, the understanding of these has just been like, really revolutionized by sort of theory coming from physics on spin glasses and the cavity method, and so a lot's now known about, and including a lot mathematically, is known about the structure of problems like random colorings on random graphs, or random k-sat, or the hardcore model on random graphs. And so you've probably heard this like story lots of times, but sort of say if you take, to fix a problem, the space of colorings on a random graph, as you change, say, the average degree in the graph, then when the average degree is small, you expect most of the colorings to be in one connected component, where you can think of two colorings as being sort of adjacent if they differ at just one vertex or a small number of vertices. But as the average degree exceeds some critical value, it splits into exponentially many small clusters. And this was proved rigorously, I think, for k-sat by Mezard, Moore, and Zecchina, and also more generally for I think, by Aklioptis and Kojaralon. Yeah, and there are other transitions that go on as well. Sorry, yeah.
I missed something. What do you mean the colors cluster?
Okay, so you have a random graph, and you can look at all the colorings of that graph, and you can talk about.
You say it's similar if they different few.
Yeah.
Different things.
Yeah.
I see. So what's D here?
D would be the average degree of, say, your random graph. And so if
How many colors you're hoping to color this?
so a fixed number of colors, and then
So D sub
Like
C
you
is
mean
some
like
function of C.
7. Fixed meaning constant?
yeah, so some, yeah.
That's your C.
No, so okay, so you'll take some fixed k and look at k colorings on graphs, and so if the average degree is if the average degree is, I think, about K-log, so DC.
If the average degree is really high, you expect not to be able to color it with so few colors.
Right, so then it becomes a harder problem. If the average degree is very small compared to the number of colors, then every stupid algorithm will succeed, and then all the coloring are kind of close to each other because
If the average degree is high, every stupid algorithm will succeed. I point out the obvious reason why you couldn't color that many colors, and I'm done. Like you want a 3-color, I give you a 4-click, and I'm done. Right, that's the...
no, then there is no colors at all. I guess that's the rightmost thing.
Yes.
But I mean, there is a range where the stupid algorithm stops working, but you still have coloring, I guess.
Yeah, thank you. And I think this degree will be something like K log K.
And I guess maybe also it's obvious that if you have like much more colors than the degree, then probably you can switch color in one vertex without ruining too much what happens around. So
yeah,
so that's why it's connected.
Yeah. Right. And all the kind of basic Markov chain Monte Carlo algorithms require you to have, I guess the proofs, the analyses of the basic Markov chain Monte Carlo algorithms require you to be in the situation where you have more colors than the average degree. And whereas in this clustering transition occurs where you have many more, the average degree is much larger than the number of colors. And so the first point was, below this, the kind of, if I got that, I think this, almost. Right, yeah. So when the average degree is smaller than this critical threshold, kind of the basic, like a sensible kind of a greedy algorithm works. And beyond this clustering threshold, like just the structure that you get shows that sort of kind of local search or MCMC algorithms have to, like, just can't succeed. But sort of better performance comes from these, from the new belief and survey propagation algorithms. And I guess for the latest on that, you should talk to Ricardo, or I won't go into that. But the basic question, which sort of isn't addressed in this form, is like, when is it hard to, or is there some range in which it's hard to find colorings? And in some sense, for complexity theory, this is a difficult question because it's a question about hardness on average, and there's kind of not really a theory developed enough to sort of tackle that kind of question. At least it could be the case that you can always solve it on average, but yeah. So that's what I wanted to say about random constraint satisfaction problems. Another aspect in which phase transitions play a big role is Markov chain Monte Carlo algorithms that people use to sample from distributions, and this is one of my favorite topics. And so I'll tell you like a bit about what's known for the Ising model. So the Ising model is another one of these systems where you have sort of a bunch of, so a graph, so this will just be, these will be the vertices of the graphs, and and it's a distribution over configurations, which are sort of assignments of pluses and minuses to each of the vertices. And it's weighted so that you give more weight to configurations that have more pluses next to pluses or minuses next to minuses. So it's think a model of like the magnetics in a chunk of iron or something like that. And so the question is, can you sample or approximately sample from this distribution? And one of the main ways, or at least the most basic way people, most basic Markov chain people would look at would be the Glauber dynamics or the Metropolis-Hastings algorithm, just because these are kind of algorithms used for sort of almost like for a really wide class of these kind of Markov random field type models. Or for, and so it's a Markov chain, and in one step you just pick a random vertex, look at the spins at the neighboring vertices, and then based on that work out what the conditional distribution of your vertex should be and update it according to that probability distribution. And so the dynamics will be reversible and stationary with respect to this distribution. So you do enough steps of this and you end up with a sample from the that's close to the stationary distribution. And the basic question is, how long does that take? And so if it's polynomial, that would be an efficient way of doing it. If it's exponential, that's not so efficient. So, and the main thing I want to talk about is now the relationship with, this has a close relationship to the phase transitions of the Ising model, so that doesn't quite appear as well on this screen. But so if these black and white dots are the pluses and minuses, for high temperatures, so this will be when the interactions between neighboring vertices are weak, there's no real structure to it, and vertices that are a long way away are basically independent.
So high temperature means that this beta
is small.
Beta is small?
Close to zero. Small even close to zero.
Close to zero, so it's almost like the uniform distribution just over strings or something.
Yeah. And so beta is the inverse temperature, so that's why it goes the other way around. And then when beta is large, you'd have the low temperature distribution. And for, I guess, almost 70 years, people have known where, for the two-dimensional lattice, where the critical value occurs. And some of the most interesting mathematics occurs in understanding the phenomena at the critical temperature. There's just kind of an aside, and so Smirnov won the Fields Medal this year partly for work on understanding the interface between like what the plus cluster and the minus cluster look like here, and showing a convergence of that to the SLE, the Schramm-Loebner evolution.
So let me just make sure that I understand this graph. So right now, a base graph is the two-dimensional lattice?
Yeah, so this is the two-dimensional lattice, and it's got a boundary condition that's plus on the bottom and minus on the top. And this is the Ising model at three different temperatures.
So this is just a typical, so this is just a typical sample from that model?
Yeah.
Okay.
And so, just to visually demonstrate the phase transition. So from unstructured to kind of critical structure to very structured, I guess, and very strong correlations at low temperature. Okay.
It's very, very low temperature. It will be like completely ones or completely zeros, right?
Yeah. And the reason why it's kind of half ones and half zeros is because of the boundary condition.
It can be like all ones and ignore the boundary. I mean, if the temperature is very, very low.
Yeah, and so that's a good point. And at low temperature, say if you have no boundary condition, then the two most likely states will be either mainly all plus or mainly all minus. And so this has a bimodal distribution. And that leads to the mixing time being exponentially large at low temperatures. And this was in 2 dimensions originally shown by Jennifer and others quite a while ago. At high temperatures, it's known to mix very quickly, just so the volume times log of the volume, which is basically how many updates you need to do to make sure that you hit every vertex at least a constant number of times. And at the critical temperature, it's polynomial in n. And so this was recent work with Eyal Lubetsky, one of my co-authors in, one of my colleagues at Microsoft in Redmond. So here the phase transition plays like sort of central role in the how long this Markov chain takes to mix. And you get similar results on other trees and other graphs. But this isn't a computational transition. So there's a different way of approaching the problem by Theorem and Sinclair, which can actually sample from the Ising model at any temperature. Yeah. And this is done by kind of reducing the problem to, or equating the problem with a different problem and then running a Markov chain on that one. And also, yeah, so so the point is that phase transitions don't always, even when it looks like it might affect the computational problem, doesn't always. You can also look at the Potts model, which is the same thing except with more than 2 states. And here, a result of Jennifer and Christian and about 5 other co-authors showed that sort of understood when the Potts model on the lattice was rapid mixing or not, in polynomial time or not. And at least when the number of when Q the number of different states you can have is large, then it's exponentially slow. And for the Potts model, it's not known whether or not on general graphs there's an algorithm for, say, approximately sampling from it, or approximating the partition function. And yeah.
When you say exponentially small and exponentially, how would it, exponentially the number of vertices? And where does Q, I mean, because Q is large.
Sorry, when Q is, yeah, larger than some fixed constant.
Okay.
Yeah.
I see. Then
Yeah.
the number of vertices.
So it behaves very differently from Q equals 2.
Yeah, yeah.
And this is also for the for the lattice, for the.
So this result is for the lattice. Yeah. Well, okay. So I think the result is for any dimension d greater than or equal to 2, there's a q of d such that if q is greater than or equal to q of d, then it's exponentially slow in, I think, exponential in n to the d minus 1. So, okay. And so the latest news on the Potts model is that, approximating the partition function for the Potts model is sort of at least as hard. Oh, and when I say the partition, as this complexity class here, which is one that Theorem and Sinclair, Theorem and maybe Goldberg created about 10 years ago, which is equivalent to, can you approximately count independent sets on bipartite graphs? And there are, and they've shown that so counting independent sets on bipartite graphs are RH pi1 complete, and there are various other ones in this complexity class as well, including sampling from the Ising model, where you sort of put an external field, so you bias some of the vertices to be more likely to be plus or more likely to be minus. Okay, and so
Function, you mean just the number of them, or?
right, so yeah, I guess I haven't defined this. It's basically the normalizing constant in the probability distribution, which is associated with the kind of the counting problem.
Like a weighted sum.
Yeah, yeah.
Computing the number harder than sampling, or I mean, how is it related to?
It's
the same?
it's harder, so it's at least as hard as approximately counting independent sets on bipartite graph.
What is it related to with the problem of sampling from the distribution?
Okay. So if you can approximate the partition function for something like the Potts model, then there's on sort of on the particular graph and any sort of on family of like subsets of the vertices as well, then there's a result saying that you can approximately sample from it. And if you can approximately sample from it, you can approximate this. So they're equivalent as long as they're on a sort of large enough family of graphs. Okay. Okay. So the main message of this section was, oh, sorry.
This complexity class, are there any relations to other, or good conjectures about its relation to other complexities?
Yeah, so I mean, it's not clear that there isn't just a polynomial time algorithm for doing all of them. So I was just looking at their paper the other day, and they said something like, well, we've had this around for 10 years, so maybe that's evidence that there's no good way of doing it. I don't know, but...
Is there a big difference between counting the number of independent sets in bipartite graphs and graphs?
Yeah. Right, because... well, I'll be getting onto independent sets in about one slide time, but the main difference is that kind of in independent sets, like...
For one, you can do it efficiently, right? I mean, in polynomial, we can compute the largest independent set in polynomial.
Independent, it's like
I mean, it's vertex cover, right? Vertex cover and bipartite process. It's just the same as mentioning.
Okay.
You can define, you're saying.
Yeah, just like.
Yes.
I mean, but it's a
And it's
different.
harder in general.
Independent set is fine.
Yeah. Okay. Yeah, and so I guess typically in a bipartite graph, like, okay, so so now I'll be talking about counting in, independent sets, and so there's a big difference, say, between a random bipartite graph, or the independent sets on random bipartite graphs, and just general random graphs, because for random bipartite graph, the biggest independent sets, you just choose one side of the bipartite graph or the other. Okay, so so now the hardcore model is just a probability distribution over independent sets on the graph. So and it's for some parameter lambda called the fugacity, and I also don't know what fugacity means, but you say that the weight you give to an independent set would be proportional to lambda to the power of its size. So when lambda is a small positive constant, most of the mass is on small independent sets. And when lambda is big, most of the mass is on big independent sets. And so this is samples of the hardcore model for just on the square lattice again for different values of lambda. And the different colors indicate the parity of the vertices. So whether or not they're like on the, if you look at it as a checkerboard, whether or not they're on the black or white squares.
Lambda is larger than 1 or smaller than 1?
Either.
Could be either.
Yeah, anything that's positive.
Okay.
And so if lambda equals 1, you'll just get the uniform distribution over independent sets. I'll be interested in the question of approximating z, the partition function, which is just, so in the case of lambda equals 1, just the total number of independent sets. And for other values of lambda, it's a weighted sum of independent sets. And sort of as I mentioned a bit before, like say for the hardcore model, if you can approximate z to within a good enough polynomial factor on, say, a graph and all of its induced subgraphs, then you can use that to what am I saying? You can use that to sample from the approximately sample from the hardcore model. Approximating z is equivalent to approximately sampling. Now, visually, I want to suggest that there's a phase transition here as you're increasing the values of lambda from 1/2 up to 5. Yeah, so these are different, these are just instances randomly generated from the hardcore model for different values of lambda, just on a square, like a torus, I think. And the different colors indicate sort of the like the parity of the vertex, because like the lattice is a bipartite graph, so which side of it it's on. Okay.
I'm confused. So this is supposed to be an independent set.
Yeah. So the edges and the vertices that aren't chosen aren't drawn in here, but this would be like if you just highlighted all of the vertices that you from the independent set on the lattice.
You see here vertices that seem like to have the same color and be neighbors of one another.
So the diagonals, the edges are on the diagonal.
But they're also white vertices, right? So I think the color would, I mean, I'm not sure. I mean, so what does the vertex being white mean? I mean, not color.
It's not in the set.
So yeah, I mean, I guess at every vertex, right. So I guess this is what I get for using other people's pictures, but so.
When lambda is high, you have two solutions that are very probable. All the even spots or all the odd spots.
Yeah.
So
yeah.
That's why that's the last two pictures
yeah.
that you see. And you'll never see a red one next to a blue one because they can't be neighbors.
Okay, by the coloring thing, it's all by definition it's independent set, because something that's not independent set will have two colors in the same box or something like that.
Yeah, yeah. If you,
I guess.
Yeah, if it wasn't an independent set, these would overlap. And I think that's where the kind of looking at the hardcore model came from originally, from the physics point of view, that these were kind of particles that sort of are solid and can't be too close to each other. And that's so, yeah. Okay. Anyway, the point I want you to take away from the diagram is that, when lambda is small, you basically have equal numbers of vertices on each side, and when lambda is large, you have either mainly from one or mainly from the other. And I think the phase transition is thought to occur somewhere around lambda equals 3 and 3.6. Okay. And so when lambda is small, you can show that there's sort of good decay of correlation. Whether or not this vertex is in the independent set is more or less independent of vertices a long way away. On the other hand, when lambda is large, it has to make a global choice of saying, well, we have either mainly the even or mainly the odd vertices. And so knowing what's happening in one part of the graph pretty much tells you what's happening in a distant part of the graph. So this is the kind of phase transition it exhibits. Just because so if you sort of just want to choose a independent set with a small density, or say you were like packing a box where like you just putting in a few articles, things in it, then you can do it any way you want. But if it's really full, you have to have the right structure. There has to be a structure to the way it's being packed, and so there's a transition. So the actual threshold isn't known, but when on the deregular tree, you can calculate exactly where the sort of analogous threshold occurs, which is this, and that's that you can get just by solving a simple kind of recursion. Okay. And the behavior of the hardcore model on the infinite deregular tree is sort of plays a pivotal role in counting for general deregular graphs, or graphs of maximum degree D. So this is the threshold for the tree is the important one. Okay. Just what was known previously. So Greenhill showed that on graphs whose largest degree was, on the class of graphs of maximum degree 3, it's number p hard to exactly count the independent sets. And so the best you can really hope for is to approximately count independent sets. And Weitz developed a actually deterministic algorithm for approximating the partition function based on a computational tree approach. So by looking at the tree of self-avoiding walks on the graph, and when lambda is less than this critical value lambda c, there's a deterministic polynomial time algorithm for approximating the partition function on the class of graphs of maximum degree D. On the other hand, when lambda is really big, you'd expect the problem to be hard, because well, when lambda's really big, the hardcore model will put most of its mass on independent sets which are close to the maximum independent set, and like finding, even on sparse graphs, finding the largest independent set is hard, and I think even approximating it is also hard. So so you can't expect to yeah, you can't expect to be able to do it, approximate Z for really large values of lambda. And Luby and Vigoda first showed this, and then Diaphrys and Geram improved their estimates. And in the special case of lambda equals 1, showed that there's no algorithm for approximately counting just unweighted independent sets on graphs of maximum degree 25. Okay. And now I want to tell you about a more recent work of Mossel, Weitz, and Wormald, where they looked at what random graph, they looked at the hardcore model just on random bipartite deregular graphs. And here the behavior of the hardcore model exhibits a phase transition exactly at lambda c. So when lambda is less than the critical value lambda c, if you take the hardcore model, generate a random independent set on your random bipartite graph, most of the time you'll have approximately equal numbers of vertices on both sides of the graph. On the other hand, when lambda is bigger than the critical value, but their proof only works when it's just slightly bigger than the critical value, they showed that you either have significantly more on one side or significantly more on the other side, like a linear amount extra. And so, was I going to? Yeah, and as a result, they showed that any sort of local reversible Markov chain must take exponentially long to mix, because the balanced independent sets have exponentially small probability. So the distribution looks kind of bimodal, and it takes an exponential amount of time in the number of vertices to go from one of the modes to the other. Okay. And based on this result, they made the following conjecture, that you should have, when lambda is greater than this critical value, that it should be, unless there should be no polynomial time algorithm for approximately counting or approximating the partition function, unless NP equals P. Yeah, and so in the special case of lambda equals 1, you can't do it on graphs, the class of graphs of maximum degree 6, whereas it is known that you can on the class of maximum degree 5. And so most of this is, and so the main result of the talk is that this is mostly verified, again with the same condition that they had, that only up to lambda slightly bigger than the critical value. But unless p equals np, there's no polynomial time algorithm for approximating the partition function, for this range of lambda. And I can also say, but in the case where lambda equals 1 and d equals 6, it's also hard. So that's the, so actually, so I don't have this in the paper, but it's actually hard even up to like a factor of 1 plus epsilon to the n. So, but yeah, certainly up to a polynomial factor, and
I believe this epsilon is just a technical condition, that the truth is that
this,
it's just
this is a technical condition for, you need to be able to work out or estimate the second moment of the partition function. And to do that, you have to show that some complicated function has its maxima in the right places. And if you can do that, then you can remove this restriction. And there's no reason to believe that this is real. Okay. So I'll tell you, so the proof is really in two parts. There's a question about studying the structure of independent sets on random bipartite graphs, which I don't want to say much about, and then how you use those results about to do the reduction. Okay, so the basic proof will be along the lines of taking a random bipartite graph, which is mostly d-regular, but has a few vertices of degree d-1. And I need these just so that you can connect these gadgets up to other ones without increasing the maximum degree. But it doesn't. This change doesn't really affect the analysis that Mossel, Weitz, and Wormald did. You still have, when lambda's sort of in this range, you still have either more on one side or more on the other, and like substantially more. And so I'll call this the phase of the independent set. So whether or not you have more on the top half or more on the bottom half. And now the critical estimate to make this work is that conditional on the phase, these vertices of degree d-1 are, whether or not they're in the independent set, is essentially independent of each other. So unconditionally, they're definitely not independent. So if it's in the plus phase, then these all have higher density, or are more likely to be in the independent set. If it's in the minus phase, they're all more likely to not be in the independent set. But when you condition on the phase, they become independent with different densities on the top and the bottom. So
if you condition on the phase being plus, then the top ones are inside with probability 0.51 independently, and the bottom ones are with probability 0.49 independently?
Yeah, and if it's the other way around, it's the probabilities are the other way around. And so the key question was establishing this, and this involved sort of a second moment method calculation over the partition function to show concentration of it, the small graph conditioning method to show even better concentration of it, and analysis of the reconstruction problem on the tree. So, what you can show is that if you pick a random vertex and look at the hardcore model on it locally, it looks like an extremal Gibbs measure, which essentially means you have very good decay of correlation within the graph, conditional on the phase. And these, because there aren't many of these degree d-1 vertices, so think like n to the 1/10 or something, these ones are all a long way away from each other, and as a result, conditional on the phase, they're basically independent.
But this thing, maybe I missed something. If lambda was smaller, this will only be more true, no?
Yes, but the point is that if lambda is smaller, it's still true, but then you don't have probabilities 0.51 and 0.49. They'll be both 0.5 and 0.5. So it's the fact that you have these two phases where you have different distributions on the top and the bottom, but conditional on the phase, they're independent. And now once you establish this, then you can do a reduction to max cut. And so so this is a randomized reduction, and so I'll solve the max cut problem on a graph H with some small polynomial number of vertices. And so for each vertex in H, I'll take one copy of the gadget, and whenever there's an edge in H, I'll add n to the beta number of edges between each of the gadgets. And now, so if you could approximate the partition function, then you could approximately sample from the distribution. And so I could ask, on this graph, what are the phases in each of these gadgets? And that will give sort of either plus or minus or top or bottom for each of these vertices. So this gives you a partition of the vertices of H into two sets. And the calculation you can do shows that, so you can basically calculate what's the chance of seeing a particular phase, and it's just determined by the cut of the graph. And the reason for this is it's much more efficient to have sort of neighboring gadgets in opposing phases, because you want higher density vertices to be connected to lower density vertices, rather than high density ones connected to high density ones and low density ones connected to low density ones. And
just complement distributions in the different gadgets, or is it
so the edges kind of. So the edges have the effect of reweighting the distribution. So if there were no extra edges here, you just have essentially the uniform distribution on the phases. Adding them in, you reweight the distribution on them, and and the probability, and you can work out exactly that factor, because it's like saying, if I choose an independent set on the graph without these extra edges in, what's the probability that it remains an independent set when I add the extra ones in? And that's something you can just explicitly calculate if you know that these are conditionally independent given the phases. And so if you choose the parameters right, this puts almost all of the mass of the distribution on instances that solve the max cut, that are max cuts. And so if you can approximately sample from these graphs, you can, this reduces to the max cut. And yeah, and so one point was that someone just made yesterday was that this doesn't require the PCP theorem, whereas other, like the previous hardness results of this form tended to reduce to approximation type questions.
Because you're going to get an exact mass cut.
The exact one, not just an approximation to it. Yeah.
What you're saying in some sense is that if you, say, consider the variant of the Ising model where instead of xi xj you'd add the xi times minus xj, then if you take this beta to be, that parameter to be huge enough, then the only thing you're going to get is the max cuts.
Yep.
And here, by setting up the size of the graphs, you can basically simulate that model with parameter as big as you want.
Exactly, yeah. Yeah, and so that takes me on to the next slide, which is like, so one question is, can you show a similar result for the Ising model where you allow beta to be negative? And so again, there's a uniqueness sort of threshold, and sort of morally all the same approach ought to work in that case. But there's one, and the one thing that's missing is being able to do a the right second moment method estimate, which will probably be even worse than in the hardcore model. And so for the hardcore model, if you can show the function that comes up in the second moment method has its maxima in the right place, then you can extend the hardness to all lambda greater than the critical value.
So, but with the easing model, then that should be also an example where if beta is sufficiently small, then it was known that this is exactly like exact max cut. For the same reason, you don't need the PCP there also.
Yeah, I guess so. I mean,
just the parameter then depending on the size of the
size
right,
of the
yeah. Yeah.
Yes, there is some way to do amplification like you did here.
Yeah.
Which I don't know how the red, how do people prove that red thing?
This is just because yeah, it's an approximation to max cut, so yeah. Yeah, so, and I guess you can ask, are there other models for which the approximate counting thresholds are given by phase transitions? And so the most interesting example to prove, I think, would be colorings. But here the problem is that the algorithms for approximately counting colorings are a long way from what you might predict from the phase transitions of the sort of coloring model on the deregular tree, say. So I think the best result on completely general graphs is by Vigoda, which says that you need at least, you can do it if you have 11 on 6 times the maximum degree number of colors. But the truth might potentially be just the maximum degree plus 2. And yeah, so thanks for listening.
So in the kind of problems involving phase transitions, there's often a gap between what you can rigorously prove, mathematically prove, and what you can say non-rigorously with methods from physics like a replica method or field approximation and such. So regarding the kind of problems that you discussed, is there such a gap that maybe you can say something stronger or more general but non-rigorously?
So, yeah, I'm trying to think. There should be models in which you should be able to make predictions based on sort of what you think of the behavior of the phase transitions, where you don't know that. But I mean, I guess if I was bold enough, I'd conjecture that the coloring one was an example of this, where I guess you know the phase transition in that, but there's there's a long way to. So the reason why at least some people conjecture that you can count colorings on degree d-2 is because on trees you have sort of good spatial mixing of the random coloring model, and that in some sense these should be the worst case for decay of correlation, and so hopefully things work out on general graphs too. So one of the, for the hardcore model and for the, I think also for the antiferromagnetic easing model, this will kind of shows that tree-like graphs are the worst case instances, and if you have, because the algorithmic bound which comes from Weitz's construction, if say nowhere it looks exactly like a tree, then you could do slightly better than this lambda c. So yeah, so to get to this, it's like at least some of the graph has to be tree-like. I don't know. So potentially there are a lot of there are more predictions you could make based on physical intuition as well. I'm sure.
So do these physical intuition more or less correspond to the intuition that trees are the worst case?
So so the first problem I started doing with Elkanan was one which was basically to show that for decay of correlation for general systems, trees are the worst cases, and you can come up with a sort of somewhat contrived example where at least for the uniqueness threshold of models, the tree isn't the worst case. But it seems like for reasonable systems, at least there aren't any counterexamples to that. So, yeah.
Yeah. Did you say how you choose the gadget is?
Sorry?
How you choose the gadget is?
Oh, sorry. So it's basically just well, effectively, it's like just choosing a random bipartite graph where you force these vertices to have degree d and these vertices to have degree d minus 1. So, yeah, you could even just do it by taking a random deregular bipartite graph and breaking a few of the bonds, and that would give you like a construction that would work. I think in the paper I sort of did it in a bit more complicated way just because it made the analysis a bit easier, but these ones but just choosing them randomly will work. And the random graphs give you locally tree-like graphs, which is what you need, and expanders as well, which is also important.
So the proof involves somewhat like a worst-case graph with analysis of changing lambda. So
yeah, so I mean it's very much like worst case, like it's like small random gadgets connected together in a worst case way.
But there's nothing for random.
No.
Random
No. Yeah, and I think that would require a huge breakthrough probably.
So in some sense you're amplifying the temperature or something like that by doing these gadgets.
Exactly, yeah.
So worrying about the degree, I mean, if the degree is like 1, there should be hardness, right? I mean, so what was the condition on the degree in your theorem?
So, sorry?
What was the condition on the degree? I mean, somehow if you say d equals to 1, that doesn't make much sense. Or
d equals, so d greater than or equal to 3?
Oh, so there's some fixed lower bound then.
So for the, I mean, you mean in the results or?
Yes, for every d at least 3, that's the result.
Oh, sorry. Yeah, no. Well, on graphs of maximum degree 2, they're not very interesting graphs. So, yeah, I left that out.
But it's just some absolute lower bound, and I mean 3, and then it looks.
Yeah, 3 is like when these random graphs start to be connected and have all the right properties that you want. Okay.